least disturbance to the environment around us, and that too with the social cause. So what I believe that welcoming you all to this FDP for 5 days, there will be a tremendous interchange of the knowledge between the experts and the participants. And I hope that the collaboration between all the participants and experts go up to that level that we come out with certain fruitful products or the projects which will be helpful for the society and nation at large. So once again, I welcome all of you, and I wish all the very best to all the participants, to the organizing committee of the department, and wishing all the best to the participants. And I welcome again all the experts, Dr. Vinod sir, and all the experts to come in the coming sessions. And wishing you again all the very best. Happy learning, and over to you, Pulkit.
Thank you so much, sir, for your wise words. Now, Dr. Vinod Kumar Singh, he is an assistant professor in the Department of Mechanical Engineering at NIT Kurukshetra. He has more than 5 years of teaching and research experience. He obtained more than 5 years of teaching and research experience. He obtained his PhD degree from the discipline of Mechanical Engineering, IIT Indore. He received his MTech from the NIT Raipur itself. His research interests are the measurement of thermodynamic and thermophysical properties of solid-state energy storage minerals, carbon dioxide capture, absorption-based heating and cooling systems, thermal energy storage systems, and phase change materials. He has published more than 30 papers in peer-reviewed international journals and proceedings of international and national conferences. Sir, we beseech you to join us on the screen. Sir, please.
Yeah, thank you very much, Pulkit.
Thank you, sir.
Please allow to me share my content.
Okay, sir.
I think my screen is visual, all of you.
Yes, sir. It is visible.
Okay. Thank you very much, HOD sir, Mayank sir, and Pulkit for giving a nice introduction. Okay.
Thank you, sir.
Shall I start my presentation or
No, sir, we are ready. You can start, sir.
Okay. Good afternoon, all of you.
Good afternoon, sir.
Today I'm going to present the topic related to development of CO2-based adsorption cooling system. Before starting the my presentation, I will little bit discuss before starting our development of CO2-based adsorption cooling system. For adsorption-based cooling system, the designing of adsorption-based cooling system is required some fundamental parameters like adsorption, isotherm, kinetics, thermodynamic properties, and operating condition. Based on these parameter, then we can go for the designing of adsorption-based cooling system. Okay. Before I am going to direct for the adsorption-based cooling system, I will start with the basic fundamentals of what is the adsorption and why I am choosing for this topic. Okay. And basically this work is related to my PhD work, and this work is basically divided into 4 folds. One is the measurement of adsorption isotherms, and then modeling of adsorption isotherms, then measurement and adsorption kinetics, thermodynamic analysis of CO2-based adsorption phase and gaseous phase, as well as the application part is related to adsorption-based cooling system. Today I am going to present, these are the contents I will cover during my presentation: introduction and objectives of the study, physical characterization of the adsorbents, measurement and modeling of CO2 adsorption isotherm, measurement and modeling of CO2 adsorption kinetics, thermodynamic analysis of CO2 adsorption for gaseous and observed phase, single phase CO2-based adsorption-based cooling system, then comparison of single stage and single effect two-stage CO2-based adsorption cooling system, and last is the conclusions. Okay. I think all of you are aware that the development of modern civilization has led to continuous utilization of fossil fuels. As shown in figure 1, you can see still we can depend on the fossil fuels for the development of energy or electricity. As a consequences for as a consequences to utilization or continuous utilization of fossil fuels, the CO2 concentration level is increased day by day, and you can see in the second figure the CO2 concentration levels are increasing day by day, and up to now the CO2 concentration level in the atmosphere is approximately 409 ppm parts per million. And the International Panel on Climate Change (IPC) estimate the average CO2 concentration level may rise to 570 ppm by the end of the 2000 year, causing an increasing the mean sea level height is approx to 3.8 meter, and the rise in the global average temperature of about 1.9 degrees centigrade. Then the several scientists are suggested so many options to reduce the CO2 concentration level in the atmosphere. One is the scientists are suggested to improve the energy efficiency for the existing system, and second one by using the renewable energy, and third one is the capturing the CO2. For increasing the energy efficiency for the existing existing system is very difficult, and renewable energy solely by using nowadays increasing the little bit confidence in the renewable energy. But suppose we want to now how to reduce the CO2 concentration, then the only one option is available for the reducing the CO2 concentration level to capturing the CO2. But the CO2 capture and sequestration is not a solution and is not a silver bullet. It may be solve the problem for the CO2 concentration level in the atmosphere. Now I will move into the second slide. Now coming to the after selecting the CO2 capture and sequestration, then the next question it will come: which technology you have choosing for reducing the CO2 concentration level in the atmosphere? In nowadays, adsorption, chemical looping, gas separation, or microalgae. These are the some technologies are available. With the help of these technologies, you can reduce the CO2 concentration level in the atmosphere. But as compared to other technology, CO2 adsorption technology having some advantages such as increased CO2 carrying capacity, reduction in cost of CO2 separation, lower regeneration energy requirement, and minimum pressure drop as compared to other technology. Now, coming to the first question here: what is the adsorption? Because I always I am next all the slides I am talking about the adsorbent, adsorbate. What is this one? Here, adsorption mechanism is the basically here I am using here CO2 as a adsorbate. The CO2 molecules are interacted on the pores of the solid adsorbent. It means these CO2 molecules are interacted on the surface of the adsorbent. That is called the adsorption process. And suppose I am removing these CO2 molecules on the surface of the adsorbent, that is called the desorption process. Okay. After selecting the adsorption technology, the next question is coming in our mind: how to select the adsorbent? Because adsorbent is playing an important role in the case of adsorption technology. Here, the some criteria selection criteria is given. Based on these selection criteria, you can choose the adsorbent. First selection criteria, you can check the high CO2 carrying capacity. High surface material, high surface area adsorbent material you can choose. Fast kinetics, high CO2 selectivity, thermal stability, low cost. Low cost is the important one, and the scientists are given. Suppose is less than 300 or 250 rupees material, then you can choose that as a solid adsorbent, because our main motto to reduce the CO2 concentration in the atmosphere. We are not going for the high cost material. We can go for the low cost material. And then after this, I will start go for the third one. I am during my PhD, I have worked so many materials here, but today presentation I am only presenting activated carbon because activated carbon is low cost material, easily available, and you can prepare easily by using any best materials. Okay. Now, what is the benefit of the activated carbon? Activated carbon is a highly porous, amorphous solid consisting of microcrystalline with a graphite lattice, usually prepared in small pellets in powder form. Okay, and the activated carbon is you can take the any best product as a carbon, then you can activate that carbon, that is called activated carbon, by using the steam or CO2. You just to flow the steam and CO2 at particular temperature, then you can change the carbon in form of activated carbon. Here, the activated carbon normally made by the thermal composition of carbonaceous material, including coal, bituminous and substituted lignite, peat, wood, and nutshell, followed by the activation. It may be the physical activation and chemical activation. Suppose you can go for the physical activation. The binding of the adsorbent is weak, and is here in this case the van der Waals forces come into the picture here. And suppose you can go for the chemical activation. In that case, the bonding between the adsorbent is very strong, and it is very difficult to detach the CO2 molecules on the surface of the adsorbent. Activation, you can go for either steam or carbon dioxide elevated temperature. Temperature goes for the is given the range for the 700 to 1100 degrees centigrade. But you can always check. Suppose you can go for the temperature level 700 degrees centigrade. After activation, temperature is 700 degrees centigrade, and after activation, you can check the properties of the activated carbon by using some surface characterization techniques. And each temperature 10 20 degrees 30 degree, and you can check and find out the best possible activation temperature. During my PhD, I have using here 4 activated carbon. One is the Norit RB3, Norit Darko 100 mesh size, the Norit Darko 12 into 20 US mesh size, and coconut cell based activated carbon. What is the advantage by using the activated carbon? High thermal stability, fast kinetics, high surface area, pore size distribution is good, low cost. And what is the application area? Separation and purification of gas storage system, adsorption based heating and cooling system, energy storage system. These are the some applications where you can use the activated carbon. The next question it will come, why you are capturing the CO2? You can see in this diagram, the capture CO2 is using all the applications. But as a mechanical engineer, I will go for the refrigeration side. I will not go for any other side. Nowadays, ONGC IOCL is also using the capture CO2 and then producing the more oil. Okay, more fuel recovery by using the capture CO2. You can see a capture CO2. You can use all the areas, biological conversion, food products, as agent, suppression, fire extinguisher. In the case of chemical industry for producing the methane, urea, carbon monoxide, methane, all these are, you can see the capture CO2. You can use in the all the applications. And but I will choose only as a mechanical engineer, I will choose the refrigerant, CO2 as a refrigerant, and then based on this CO2 refrigerant, I have designed the 2 systems, that is the single state CO2 based adsorption cooling system, single effect double state CO2 based adsorption cooling system. I will move into the next slide. Based on the literature review, I have set the objectives of these studies. First objective, to measure the adsorption isotherm. How to measure the adsorption isotherm? Then I fabricate an experimental setup for the measurement of CO2 adsorption isotherm and activated carbon. Second, for the in the case of kinetics, again I have fabricated an experimental setup for the measurement of CO2 adsorption kinetics of activated carbon. After estimating the adsorption isotherm and kinetics, the next parameter is important, the thermodynamics properties. because while designing of any adsorption based gas storage cooling system, thermodynamic properties playing an important role. And in the case to here, I have estimated the thermodynamic properties for both the phase, is the gaseous phase and adsorbed phase, as well as the subcritical phase and supercritical phase of CO2. And the fourth objective to evaluate the performance of single stage adsorption cooling system in terms of specific cooling effect and coefficient of performance for CO2 activated carbon pairs at different regeneration and evaporator temperature, and to compare the performance evaluation of single stage single effect two stage cooling cycle in terms of specific cooling effect, coefficient of performance for CO2 coconut cell based activated carbon pair at different regeneration and evaporator temperature. Before starting my objective, then before I will find out the properties of the adjournment by using the some standard characterization. And here this is the 4 activated carbon I am using here. First I will go for the BT analysis. Why I am going to BT analysis? Because this is with the help of this BT analysis you can understand the behavior of the adjournment, and you can also find out the pore volume, micropore volume, surface area, longitudinal surface area, BT surface area, and with the help of BT analysis also we can find out the pore size distribution. And coming to the figure 1 here, this is the graph between the volume absorbed of nitrogen as versus the relative pressure. And now we can find out with this diagram the properties like surface area, micropore volume, mesopore volume, total pore volume, average pore diameter, pore size distribution of adjournments are characterized by using the gas adsorption analyzer ASAP 2010 instrument I have using during my PhD through desorption of liquid nitrogen at 77 Kelvin. This analysis I have performed at 77 Kelvin temperature just to and adsorbing the nitrogen, and because nitrogen is a carrier gas and nitrogen is generally not adsorbing the any material in suppose in the case of activated carbon here, the activated carbon is basically not adsorbing the nitrogen. That's why I am using this as a nitrogen as a carrier gas. And before beginning of the adsorbment and desorption process of nitrogen measurement, the adsorbent samples are degassed at 150 degrees centigrade or more than 200 degrees centigrade. Because why I am degassing at that temperature? Because just to remove the moisture present moisture present in the adsorbent. And you can see here the diagram is showing some different phases. You can see in the AC1 is given the first activated carbon, AC2 is the second activated carbon, AC3 is the third one, and fourth one is the coconut cell based activated carbon. You can see the first one and the last one is showing the micro volume region, and this is the generally initially is increasing and then is getting the equilibrium stage and getting the saturated. And the second one you can see the different phase, and this is the generally in the case of adsorption desorption is follow the same path. Suppose not following the same path, the hysteresis come into the picture, as hysteresis is one of the laws. And then you can see the AC1 and the coconut cell based activated carbon is follow the same path, but the other two activated carbon is not follow the same path. And based on this experiment, we have I have find out the surface area. Here basically we can talk about the two types of surface area. One is the BET surface area and second one is the longitudinal surface area. Based on this surface area, we can choose the activated carbon. Suppose higher the surface area is better for the adsorption. Okay. Now with the help of second diagram, with the help of this diagram, we can find out the pore volume. Okay. Here, this is based on this experiment. You can see the table 1, the physical properties of activated carbon, and the BT surface area longitudinal, total pore volume, micro, meso, and fraction of the micro volume, average pore diameter, average particle size. All these parameters I have find out with the help of PET analysis. Now, coming to the second here, the Fourier transform infrared spectrography. Why this analysis is important? Based on this analysis, you can find out the chemical bondings, chemical scratching between the at different wave level. This graph is showing the transmitters versus the wave number, and here I perform the experiments at 400 to 4000 wave number, and I find out that at different chemical bondings, generally C double bond O, single bond oxygen, single carbon and hydrogen bonding, oxygen hydrogen bonding. You can see generally in the case of activated carbon, these are the some bondings are present. And you can see after the desorption, you can see the one CO2 is also, you can find out where CO2 it will come, because due to the adsorption, some molecules are available on the surface of the adsorbent. Now with the help of XRD, you can find out the HKL unit cell value, and you can see the peaks here. Different peaks are there, and almost at the 2 theta value is 23 to 26. In between, you can find out the peaks. And I am using the elemental analysis. With the help of this elemental analysis, I will find out the what is the carbon percentage, hydrogen, nitrogen, sulfur percentage is present in the activated carbon. And I find out the is AC1 is the highest carbon percentage. Those adsorbent you can choose where the carbon percentage is more. Suppose carbon percentage is more, then is the adsorption capacity is more. Okay. Now I am also find out the thermal stability of the material by using the thermogrametric analysis TGA. This is the experiment is versus weight loss versus temperature, and you can see the initially is up to 100 degrees centigrade or 150 degrees centigrade is the material is removing the moisture, and suppose is the more moisture is available, and you can provide the continuous at the fixed heating rate value. Suppose I am starting the experiment 25 to 800 degrees centigrade. I will giving the interval of 5 degree centigrade per minute, and then I am getting this figure, and basically this is the showing the what is the how much your material is stable. Okay, then I will go for the next analysis is the same analysis, because with the help of same analysis I am find out the texture morphology of the material, and I am also find out what is the pore diameter, what is the pore size here, and what is the particle size diameter. With the help of same analysis you can easily find out. Now I will go for the first objective, to fabricate an expander setup for CO2 adsorption isotherm measurement on activated carbon. Before going to the objective, you can choose the what is the gap of the research. I find out the most of the researchers are only performing the experiments at the limited temperature range. I will go for the temperature range is 0 degrees centigrade to 100 degrees centigrade or 80 degrees centigrade. And most of the researchers are performing the experiments at the 1 bar pressure, 2 bar pressure. But in the case of CO2 adsorption temperature, all of you know the corresponding temperature having some saturation pressure. Suppose 273 Kelvin temperature, 0 degree centigrade temperature, the saturation pressure of CO2 is approx to 34 bar. And similar to suppose you can increase the temperature, the saturation pressure will change. Okay, and based on this gap, I find out the research for reading some the published research work. Then I will find out the some research gap. Then based on this research gap, I will perform the experiments, and then I will get the data for the how much CO2 is adsorbed. Okay. Now this is the my experimenter setup. I have fabricated this experimenter setup in our heat transfer laboratory at IIT Indore, and this is the volumetric setup as a generally two types of methods are available. With the help of these two methods, you can easily find out the adsorption capacity. Either you can go for the volumetric analysis or gravimetric analysis. What is the difference between the volumetric and gravimetric analysis? In the case of gravimetric analysis is more accurate, but is the cost of the equipment is very high, is approx to 1 crore. But the same time, you can go for the volumetric analysis. You can prepare your experimenter setup is approx 20 to 25 lakh rupees, and you can find out the adsorption capacity. You can see here, these all the fittings I am using the Sage locks here, and I am using the 2 cylinders calibrated cylinder. The volume of the cylinder is here C1 and C2 is the 300 ml. And how to decide this is a 300 ml, because whatever you can use the mass of the adjournment, based on the mass of adjournment you can find out all this volume by using the mass balance equation. Now here I am the CO2 is as a adsorbent. I am using argon gas is basically we are using for the just to carrier gas and just to see the in your system is perfect or not. It means whatever you prepare the experimenter setup, and you with the help of argon gas you can check the any leakages are there or not. Okay, and first before performing the experiments you can just to activate your material. Then how to activate the material? Just to CO2 is flowing on the in this reactor. I fill the material, and this reactor I have designed based on the mass of the adjournment. This is the 5 gram to 10 gram of the material I am using during the experiments. And this is the thermostatic bath. Thermostatic bath I am using for just to maintaining the temperature, because in the case of adsorption isotherm, you can find out the graph between the adsorption equilibrium versus the pressure. You can increase the pressure, you can find out the adsorption capacity, but at the meanwhile you can just to maintain the temperature. Okay, and now you can start the experiment. Before starting the experiments, you can just to activate the material. First activation is required, and before activation you can check the system is perfect or not by using just to flowing the argon, and at the pressure of 60 to 80 bar pressure you can check your system is leak proof or not. Suppose the leak proof, then you can start the experiments. Then first step is to performing the experiment is the activation of the material. After activating the material, you can just to flowing the CO2 gas into this calibrated cylinder, and after supplying the CO2 gas, then you can close the valve B1, B5, B4, and just to supplying the CO2 in the calibrated cylinder C2, and then into the reactor. Suppose I am maintaining the temperature at 0 degree centigrade, I will go for the corresponding to 0 degree, the saturation pressure is up to 34 bar, and then I will perform the experiment up to that pressure. Okay, and I am the step by step I am supplying the CO2, and in each step, suppose initially I am supplying the 1 bar of pressure of CO2, then the next step to I am supplying the 2 bar of pressure and up to 34 bar. And how to measure this pressure is accurate on by using this sensor. This is a pressure transducer sensor I am using to measure the pressure, and meanwhile I am also keeping the temperature measurement. I am using the K type of thermocouple here. Temperature T1, T2, T3, all these temperature I am measuring, because with the help of mass balance equation I am just to find out the how much CO2 is adsorbed. You can see this is the second figure 8 is related to the reactor used for the CO2 adsorption isotherm measurement. Here you can see this is the two tubes I have provision. One is I am just to kept K-type thermocouple inside the reactor, and second one is I am supplying the CO2 gas. And one end is showing the here that end is I am to just to fill the material, and I am also using the filter here because during the desorption I want to ensure that the adsorbent is not goes outside the reactor. Okay, and during the adsorption desorption, suppose I am just to supplying the CO2 gas into the material. What is happening inside the reactor is just to due to the exothermic reaction, the temperature is increasing, and also meantime temperature increasing, the pressure is also goes up. Then after sometimes after 2-3 minutes or 10 minutes you can get the equilibrium condition. It means we need to find out the equilibrium adsorption capacity. Now I will move into the, this one is a photographic view of the experimental setup and the reactor. And then this is the standard models are available. Based on these models I will using these isotherm models, but these models are the principle of these models are different. For in the case of longitudinal, this longitudinal adsorption isotherm model is applicable for the low pressure range side, and tooth model is go for the low pressure as well as the high pressure range. And the Dumni-Sastovo is giving the micro volume filling theory, and this adsorption isotherm equation is applicable for both the low side pressure and high side pressure. And this is again I am using the modified DA equation. All these equations I am using to after performing the experiments. And in the case of high pressure region, the CO2 is behaves like a real gas. That the real gas effect is also including during the experiments. And after experiments, you can see here the CO2 concentration level is increasing the equilibrium pressure due to the exothermic reaction. During the exothermic reaction, heat is released, and you can see initially the lower pressure side, the adsorption capacity is more because the more CO2 molecules are absorbing, because initially the more pores are available to absorbing the CO2. After fulfill all the pores, then the CO2 concentration level is going to saturated. Okay, and I am using the different models, and I simply say that this is the DA or the modified DA model is the best fitted. And I have also find out the error. What is the error between the experimental data and the model data? And I find out the experimental and model data both are in the range of plus minus 5% of error bar. You can see here all the approx to 90% of data is lies in between the plus minus 5% of error. This is again I am performing the coconut cell based activated carbon material, and I am find out the similar type of results here. And again I am finding the error analysis, and I will go for the advanced analysis for the I find out the adsorption potential and both the case DA model and modified DA model. And then we can find out in the case of modified DA model is the more accurate as compared to DA model. This is the adsorption capacity I have performed, and I will get in the case of AC coconut based first one coconut AC1 base activated carbon is giving the best adsorption capacity, and this I will compare to the other published literature, and then I will say that this is our result. My result is the more closely or is related to published results. I will go for the second objective for measurement of the adsorption kinetics, because adsorption isotherm and kinetics is based on these two properties. You can decide to adsorption based cooling system. Again, I will go for the how to choose the experiments and which temperature range you can go to perform the experiments, and what is the pressure you can choose, and all these properties you can find out with the help of kinetics analysis. I find out the activation energy, mechanism of rate controlling step, kinetic modeling. All these they come into the picture in the case of kinetics analysis. Based on the published result, I will find out the research gap. I find out the 3 research gap. One is the adsorption kinetics of CO2 and activated carbon. Different supply in pressure and temperature are rarely reported. Activation energy, different supply pressure and temperature not available. Rate controlling step during the adsorption kinetic process are rarely reported. And again, I have prepared the similar type of experimental setup for the kinetics measurement. But you can see here, I am using only the single calibrated cylinder. Based on this calibrated cylinder, I am supplying the pressure, 1 bar pressure, and I will fix the temperature 25, 35, 45, 65 degrees centigrade, and even lesser temperature also 0 degree, 5 degree, 10 degree centigrade temperature. I will supply just to supplying the CO2 at 1 bar pressure, and I will find out the how much time is required to absorbing the CO2. That is called the adsorption kinetics. And this is the photographic view of the adsorption kinetics measurement. And then you can see in this diagram here, figure 22, you can see the rate of adsorption capacity is increasing with respect to time here, and here the adsorption capacity is decreasing with the increase in the adsorption temperature, because initially the lower temperature lower temperature here, sorry, I'm saying okay, at the lower temperature here is initially you can see that rate of adsorption capacity is initially within a fraction of second is absorbing more, because initially the more pores are available, then occupying all the pores, occupying all the pores, then the CO2 molecules are get saturated, and you can find out the rate of the adsorption. And in this case, in the case of activated carbon, I find out the within 120 second the material gets saturated. It means within the 2 minutes or 120 seconds you can see the how much fast is the adsorption process. Now I will go for the adsorption capacity at different temperatures. I will find out the increasing the pressure, the adsorption capacity is decreasing. It means initially the lower pressure is getting the maximum adsorption capacity. Now I will go for the find out the activation energy. Activation energy is just the minimum energy is required to start the chemical reaction. This is the activation energy equation. With the help of this equation, I will find out the activation energy. How to find out the activation energy? By using equation third. I will plot the graph between the ln K2 versus E1 by T. Then I will find out with the help of slope, I will find out the activation energies. You can see in this diagram, ln K2 versus 1 by T. With the help of this linear graph, I will find out what is the slope. It is related to the activation energy. Okay. This is the difference showing, and you can see the activation energy is decreasing with increase the supply pressure. It means you can increase the supply pressure, the activation energy is decreasing due to the gaseous density is initially the gaseous density is more, and suppose you can go for the higher pressure side, the gaseous density is decreasing with decreasing the temperature. Okay. Now the next one is the after find out the adsorption kinetics, then we can find out what is the mechanism is available for the CO2 adsorption. Generally 5 mechanisms is available. Then I will choose out of 5 in which one in my case is playing an important role for the controlling of rate. Now initially is the film diffusion, interparticle diffusion, pore diffusion, surface diffusion, film diffusion. These are some mechanisms are available, and in the initially the interparticle and film diffusion, external diffusion these are the very fast reaction, and it is very difficult to identify this reaction, but you can easily find out the pore diffusion and surface diffusion. Okay, what is the one scientist is giving with the help of this equation you can identify which rate controlling step is available in my case. And now I will perform the experiment here by using this equation. I plot the graph what's film diffusion model versus time, and I will find out suppose this linear line is crossing this origin, then we can say that in our case is the pore diffusion or pore diffusion is the rate controlling step. But in my case you can see in the linear curve is not passing through the origin. Okay, it means this is not a pore diffusion case, and this is the just to in diffusion case. And then I will go for the kinetic analysis for the coconut cell based activated carbon. Again, I will find out the CO2 uptake is increasing with increasing time, and you can see the decreasing the temperature, the also decreasing the adsorption capacity. Okay. Now I will go for the compare the current result to the published result. I will find out the good agreement between the current result as well as the with the published result. Now I will go for the third objective to find out the thermodynamic properties for the gaseous phase as well as the absorbed phase. With the help of these thermodynamic properties like isosteric heat of adsorption, with both the case zero loading and surface loading, gives free energy, specific heat capacity, enthalpy, entropy for both gaseous and absorbed phase. As supercritical and subcritical phases, I will find out the thermodynamic properties. Again, I will go for the literature and I find out the no one is finding the thermodynamic properties at the observed phase. All the authors, all the scientists are perform the experiments and find out the or estimate the thermodynamic properties, especially in the gaseous phase. Based on the literature, I will find out the research gave the vital thermodynamic properties, namely isosteric heat of adsorption, specific heat capacity, entropy, enthalpy of CO2 adsorption of activated carbon in the observed phase at different temperature and pressure has not been estimated. Based on this one, I already explained the adsorption technology. The same concept I am using for the here for finding the adsorption thermodynamic properties of for CO2 for in the case of adsorption and gaseous phase. Now, initially whenever the CO2 molecules in the gaseous phase interacted on the solid adsorbent is making a layer. It may be the single layer or it may be the multi-layer. And initially the CO2 molecules in the gaseous phase, and after some times due to the reduction in energy, the CO2 molecules are get in the absorbed phase. That is this is the distinct phase and this is called the absorbed phase, and I am finding all the properties here for the thermodynamic properties for both the case gaseous phase, the absorbed phase, by using the heat of adsorption Clausius Kaplan equation, and with the help of Dubny-Stokov model I have prepared find out the equations for the both the case subcritical phase, supercritical phase for the in the case of entropy, enthalpy, gases gives free energy. All these equations, all these are properties I find out with the help of these two equations. Now, in the case of CO2, you can see in the figure 33. In the what is the critical point temperature in the case of CO2 is only 31.1 degree. Below this temperature is called a subcritical temperature. Above this temperature is called a supercritical temperature. Now, in this case, in the case of CO2, no boiling point temperature. Okay, and here the triple point temperature is approximately minus 56.6 degrees centigrade at 5.11 atmospheric pressure. Now, initially, I performed the experiments and with the help of longitudinal tooth model, I have plotted the graph between the LNB. LNBB is the affinity versus the 1 by temperature. Then with the help of these linear graph, with the help of slope intercept of this linear graph, I find out the isosteric heat of adsorption and the entropy. Slope is related to the enthalpy and intercept is related to entropy. Okay. And then I will perform the experiment. I have plot the graph here, LNP versus 1 by T. You can see here I am choosing the different adsorption capacity. The capacity is related to 0.1 gram of CO2 per gram of adsorbent. And I am taking the 0.1 to 1 gram of CO2 per gram of adsorbent. And this is the different cases I have I will plot the graph here, LNP versus 1 by T. With the help of this graph, linear graph, I will find out the isosteric heat of adsorption. And initially, all the scientists are published the literature. The isosteric heat of adsorption is constant with increasing the uptake. But in my result, I will find out the isosteric heat of adsorption is varies with the varies the uptake. You can see in here diagram the Longuemule model and tooth model, you can find out the constant isosteric heat of adsorption value. But by using the Clausius-Kaplan equation, I am find out the isosteric heat of adsorption is decreasing with increasing the CO2 uptake. Okay, in all the cases. Next one, in the case of estimation of thermodynamic properties of CO2 adsorption for observed phase, this is the estimation of observed phase specific volume. The equation is the BA equal to BT exponential alpha T minus TT. This is the tipple point temperature TT. T is the adsorption temperature. Alpha is a constant, and BT is the total volume. BA is the observed volume. Now we can find out the graph between the space of observed specific volume BA to temperature TA. This graph, it looks like a linear graph, but you can see this is not a linear graph. This is related to exponential graph. And now you can see here. Initially, all the scientists are said that with respect to temperature, the observed phase specific properties are constant. But during this, I am using this equation. With the help of this equation, we can say that the specific observed phase specific volume is increasing with increasing the temperature. And I am also plotting the graph. You can see the different temperatures, and you can find out the properties by using this graph. And now I am find out the very interesting graph here. You can see below the critical temperature, the isosteric heat of adsorption is decreasing with increasing the CO2 uptake. But in the case of above critical point temperature, the isosteric heat of adsorption is increasing with increasing the CO2 uptake. And I am also find out the specific heat capacity, because this is specific heat capacity is also important properties for designing of adsorption based gaseous storage system or cooling system. And you can see specific heat capacity is decreasing with increasing the equilibrium pressure, except the case third, AC activated carbon 3, because here the heterogeneity and the heterogeneity constant, activation, and the characteristics energy is more in the case of AC3. And also we can find out the observed phase entropy and enthalpy. You can see the below critical point temperature, the observed phase entropy is decreasing, increasing the CO2 uptake, and similar to the second case above critical point temperature, the observed phase entropy is increasing with increase in the temperature, similar to the entropy case. And I have compared my results to the other published result, and we can simply say that this is the good agreement between the current result to the published result. I will go for the fourth objective, to evaluate the performance of single stage cooling cycle in the terms of specific cooling effect, as seen coefficient of performance COP for activated carbon pairs at different regeneration evaporator temperature. Now you can see this is a single stage cooling system. The two is mainly two performance parameter is the specific cooling effect and the coefficient of performance. And how to design the system? I will choose the different regeneration temperature, fixed adsorption temperature, different evaporator temperature. Temperature is varies for 0 to 15 degrees centigrade, and CO2 activated carbon I am using as a adsorbent pair. Based on the literature, I find out some research gap. The effect of operating parameters on CO2 activated carbon adsorption based cooling system has been rarely reported. The performance comparison in terms of specific cooling effect and the coefficient of performance COP of the CO2 activated carbon pair single stage, single effect, two stage adsorption cooling system are also not available. Now, initially the scientists are giving the single bed adsorption cooling system. But what is the drawback for the single beds? Here, you can compare this adsorption cooling system to vapor compression refrigeration system. Here, the only difference between in the case of vapor compression system, the compressor is used, but here I am using the reactor or bed or thermal compressor, you can say that. And here in this reactor, I will fill the material as activated carbon, and other components are same: evaporator, condenser, expansion valve. And suppose you want to continuous cooling, and the single bed is not suitable, because you can find out the performance parameters COP in AC. Suppose you want to continuous cooling, then you need to two bed system at least. And during the adsorption based cooling system, generally the four processes are there. One is the pre-cooling, adsorption, preheating, desorption process. These are the four processes in the case of adsorption cooling system. These are the four thermodynamic processes. Now, the next question is come into our mind: what type of refrigerant you can use and what type of adsorbents you can nowadays. And the first, what is the adsorption? Why we can go for the adsorption based cooling system? What is the advantages for the adsorption based cooling system? In the past two few decades, maybe the 10 to 15 years before, the adsorption based cooling and heating system have got lot of attention. These systems are free of moving parts and can be operated using the low grade solar and waste heat energy. Among all the refrigerants, CO2 is one of the natural refrigerant which offers a number of advantages such as high absorption capacity, excellent thermophysical properties, inexpensive, easily available, negligible global warming potential. In the case of CO2, the global warming potential is equal to 1 and zero ozone layer depletion potential. Hence, it is more suitable for the adsorption based cooling system where the refrigerant is required not to freeze at zero below 0 degrees centigrade. In the case of CO2, is not a toxicity and is not a non-flammable case. And maybe CO2 is expected to be next generation refrigerant, and maybe the CO2 is using for the in the case of large refrigeration system and supermarket nowadays using CO2 as a refrigerant in supermarket. Most of the supermarket using the CO2 as a refrigerant, and CO2 is one of the natural refrigerant among all the refrigerants here. And the adsorbents is activated carbon is easily available, low cost material as compared to other adsorbents are available as compared to other adsorbents. Activated is suitable, and in the case of CO2 is more affinity with the activated carbon. Okay. Now, this is the case for the single stage CO2 based adsorption based cooling system. Here, the generally in this system is consisting four parts. One is the evaporator bed. Bed is the one is working as a adsorber. Second one, bed is working as a desorber, condenser, and expansion valve. And how to proceed, how to perform the experiments here. Now, in the case of pre-cooling process, and with the help of Clausius-Kaplan equation, you can draw this LNP versus 1/T diagram, and you can represent the processes: pre-cooling, adsorption, preheating, desorption process. And before now, how to proceed these processes, thermodynamic process. First, start with the pre-cooling process. Before starting the pre-cooling process, we can close the wall B1, B2, B3, and B4 wall. And now, during the pre-cooling process, the pressure is reducing condenser pressure to evaporator pressure, and by using the external cooling here, the bed is achieving up to the now the condenser pressure to evaporator pressure. After completing the pre-cooling process, now you can open the valve B1. Now this CO2 refrigerant is passes to this bed 1, and this is called the adsorption process. And during the adsorption, due to the exothermic reaction, heat is released. That heat is removing by using this cooling water. Okay, and now, after completing the adsorption process, now we can close this wall B1, and now we can increase the pressure up to the evaporator adsorption pressure to the condenser pressure, and that is called a preheating process. And after achieving the condenser pressure, then we can open the valve B2, and then this CO2 refrigerant is passes to the condenser. Condenser is a heat removal device, is just to heat is removed here, and here during this CO2 is maintaining the same condenser pressure. How to maintain this condenser temperature and pressure? By using the external source, by using the industrial waste, solar energy. By using these two things, you can easily maintain the condenser pressure and temperature. After heat removing the condenser pressure, then this is called the desorption process, and now you can close the valve V2, and then you can start this. You can by using the expansion valve, you can reduce the pressure for condenser pressure to the evaporator pressure, and the suppose in the continuous cooling case, these two bed is I have used. And during the first bed, suppose is the adsorption process, second bed is performing the desorption process, and also suppose in the first bed is the preheating process, second one is performing the pre-cooling process. This is the operation I have given in the table 6. What is the operation here? During the adsorber bed switching period, pre-cooling, adsorber 2 is preheating, all the valves are closed, similar to adsorption desorption process. Adsorption bed 2 is the adsorber 2 is the desorption, and the ball B1 is closed, ball B2 is open, then ball B3 is closed, ball B4 is open. Like this is the operation is I am giving in table 6. Now I will perform all these processes in the diagram, and the CO2 uptake versus equilibrium pressure. And here is showing that all the 4 processes, process 1 and 2 is the pre-cooling process, 2 to 3 is the adsorption, 3 to 4 is the preheating, and 4 to 1 is the desorption process. And similar to all the activated carbon, I am showing all these 4 thermodynamic process. And this is the diagram is called as a pressure concentration diagram. Again, with the help of this diagram, we can find out the specific cooling effect and the COP. Now, I am find out the specific cooling effect, and here you can see this is the different for evaporator temperature. The temperature is varies for 0 degree centigrade to 15 degree centigrade. The specific cooling effect is increasing with increasing the regeneration temperature. Why increasing this regeneration specific cooling effect? Initially, the more quantities, the difference between the Q maximum minus Q minimum is available more. There's the more heat input is available. That's why the specific cooling effect is increasing initially more, and after getting some 80 to 90 degrees centigrade, then is the getting the saturation level. Okay, and we can also find out the minimum desorption temperature corresponding to each evaporator temperature by using the equations. And similar to the COP is increasing with increase the regeneration temperature. And in the case of 15 degree evaporator temperature, we can get the maximum COP, and the COP value in the case is 0.1 to 0.15. But in the case of CO2, is the COP is less, but this is the CO2 is one of the natural refrigerant. That's why all are the nowadays all are the scientists are focused for these refrigerants. And this COP is increasing up to 70 degrees centigrade. After 70 degrees centigrade, you can see this is the COP is insignificant increasing, and up to 70 degree, the COP is increasing significant due to the initially the more heat input is available for increasing the COP. Now, this graph is showing the SE and the adsorption temperature here. Suppose you can vary the adsorption condenser temperature 25 to 40 degrees centigrade, because in the case of CO2, the critical temperature is the 31.1 degrees centigrade. Below this temperature, you can get the most COP and specific cooling effect. Where suppose you can go for above critical temperature, you can get the decreasing in nature. And I have compared this result to find out the specific cooling effect and for all the materials. Now, in the first case, I will go for the regeneration temperature up to 100 degrees centigrade. Suppose this 100 degrees centigrade temperature is not available. In that case, how to design the adsorption based cooling system based on the limiting temperature? This cycle is works for the lowest temperature around 40 to 50, 60 degrees centigrade. Also, this cycle it works, and this is the cycle is called a single stage, single effect, 2-stage cooling cycle, cooling system. And here I will use the 4 beds, because this is the just to reducing the pressure for one bed to another bed and another bed to the condenser, and similar to the condenser to the one bed to the evaporator. Basically, I am using 4 bed due to the reducing the temperature, and also reducing the temperature. Then I will use the lowest regeneration temperature. And this is the working principle is similar to the single stage cooling system. And just to find out the comparison of single stage, single effect two stage cooling system based on the PCT diagram here, and you can easily understand what is the cooling effect for bed 1 and similar to bed 3 to 4 and bed 1 to 2. Again, I find out the specific cooling effect versus regeneration temperature and the COP versus regeneration temperature, and similar trends I have obtained. And then I've also compared this COP and specific cooling effect to other published results. Then I will find out the current result is good agreement with the published results. And the conclusion for the today presentation is the CO2 uptake is significantly decreases with increase in adsorption temperature, which is attributed to the weak van der Waals forces during the adsorbate interaction. The amount of CO2 absorbed increases with increasing the supplying pressure due to the higher binding forces. Activation energy decreases with increase in the pressure due to increase of gaseous density. It may be explained that the amount of CO2 absorbed in activated carbon controlled by the film diffusion. Thermodynamic properties are evaluated at gaseous absorbed phase using the measured adsorption isotherm data. And I'm also including the real gas effect while estimating the thermodynamic properties. And it is also found that the isostatic heat of adsorption decreases with increasing the adsorption temperature at subcritical state, and opposite trend I have obtained in the supercritical region. The performance of CO2 activated carbon pairs based single stage cooling system with respect to SE and COP for different regeneration evaporator temperature estimated. And I find out the SOP specific cooling effect is approx to 25.87 kilojoule per kg, and COP is 1.1 is obtained for AC1 and CO2 respectively, in driving force temperature of 80 degree with the evaporator temperature of 50 degrees. Similar to the, I have compared both the single stage and single effect two stage cooling cycle are thermodynamic simulated and compared in terms of SE and COP for different desorption and evaporator temperature along with the adsorption temperature of 30 degree. And this is the uncertainties during the measurement. I have measured what is the accuracy for the K-type thermocouples, pressure transducer, digital weighing balance. I am using vernier caliper, and this is the error analysis I have performed. And these are the some equation I am not using during the presentation, but these are the equations, and this is the observed phase specific volume, and this is all are the mathematical equation I have derived during whenever I am deriving the estimating the thermodynamic properties. This is the cooling effect equation, its performance, all these are. Thank you. If you have any question, please ask.
Thank you so much, sir. Thank you so much, sir, for such a noble and mind-broadening session. Now, let us move towards the Q&A round. And for this, I will request you all to please ask your queries, or you can write it on chat box also. Thank you, sir.
Good morning, sir. I have a question.
Yeah, please ask, sir.
Sir, why did we only use that refrigerant which is R134A?
R134A.
Yes, sir.
What is your question?
Yes, sir. I'm talking about the refrigerant R134A. Why
Okay.
only we have used only that refrigerant? Can we use other refrigerant?
You can use the other refrigerant. Nowadays, the refrigerants are available. You can choose the major criteria. You can choose the refrigerant is the global warming potential should be 0 or approx to 0, and 0 ozone layer potential. And the third one, the toxicity should be toxicity and the flammable. Okay, non-flammable. You can choose this type of refrigerants. In the case of refrigerant R34A, the global warming potential is more, as well as the ozone depletion potential is also more.
So overall, sir, we have to work on the sustainability of the
Yes,
refrigerant.
because nowadays everyone is looking for the environment, and you can go for the sustainable. That's why everyone is looking for the natural refrigerants.
Okay, sir, I'm clear, sir. Thank you so much.
And one question is come into which parameter is affecting the activation energy. Activation energy is affecting the pressure, temperature, okay, and These are the major values. Activation, initially the activation is more at the lesser adsorption temperature. Suppose you can increasing the temperature, activation energy is decreasing. Basically the activation energy is just to the minimum energy is required to start the process. Yes, any other question?
Sir, there is one more question about Vinayak Rao, that's the Bhavya base rate. Is COP of CO2 based cooling system is same as the vapor compression system?
No. In the case of CO2 based adsorption cooling system, the COP is less. The scientists are working for how to increase the COP by using different techniques. But in the case of vapor compression cycle, you can get the more COP. And the meanwhile, suppose you can go for the vapor compression refrigeration cycle, but the problem is only the environmental problems. Our motto is to protect our environment.
Thank you, sir.
Thank you.
Now, I think there is no more questions. Now we have come to the end of this session. We would like to convey our heartiest thanks to Dr. Vinod Singh for such an exciting session. This was a supreme paradigm of why this kind of interaction is crucial. We are thankful to you, sir, for enlightening us. Thank you so much, sir.
Thank you very much. Thank you, HOD sir and Mang sir, for giving an opportunity for presenting my work.
Thank you, Vinod sir. Thank you very much.
Thank you, sir.
Be with us. Our next session will soon start at 2:30.
Okay, shall I leave?
Exactly. So you can, sir. You can.
Okay, thank you very much, all of you.
Thank you so much, sir.
Thank you, sir.
Please be patient. Our next session will soon start at 2:30 p.m. Exact. Thank you so much.